when Marco asked me to give a talk here, especially the prestigious opening keynote, I really wanted to think about what I wanted to say. I mean, there's so many prestigious speakers who's coming after me. It makes it a bit of a challenging process to do all that, to come up with something that is truly overarching, gives an overview, but yet deep enough to let you know that I actually know a little bit of what I'm talking about. So I came up with something, and that took a little bit of negotiation. Marco and I worked long and hard to make sure that this worked. Thank you very much, Marco, and the staff, and the entire staff here. He kind of said, you know, if you really want to come to beautiful Milan, you have to give a talk. So I'm very glad to be here. So I came up with something. I wanted to talk to you today specifically because you're probably one of the first conference we're going to be able to have a look at what is actually in C++17. By now, many of you guys already probably know, or you may not know. So I thought it would be appropriate as an overview to take a look at where C++17 stands, because we essentially just internally ratified it, meaning that in the last conference we sent it out to Geneva for verification for their stamp of approval. So I'm going to talk about C++17, and I'm going to give you a bit of a report card and give you my opinion as to whether is it great or is it just okay, because this is one of the controversial aspects about where C++17 stands. The other thing that I want to talk about is something I've been working on very closely. After all, the best thing about a keynote is that I can talk about the things that I know a lot about, and it's really hard for you to argue with me about that. Just kidding. Go ahead, please argue with me about it. And it's called executors, and how to do heterogeneous computing. Because this is a vision that I definitely, and I and many others have in the industry, whether you're in gaming or you're in finance. And part of that is because of my current job title. Yes, I know there's a lot of job titles here. It just pretty much means it's hard for me to get really anything done. But it does mean that I do rely on a lot of people. But one of my job titles is chair of SG14. And SG14, just to give you an idea, was a study group that was started about 2 years ago to look at effects of low latency, separate than concurrency and parallelism, especially involving the aspects of gaming, finance trading, simulations, and embedded computing. I think that this is unquestionably one of the burgeoning areas of C++. And I'm leaning towards things like Internet of Things, self-driving cars, of which my company is deeply involved in, machine learning, machine intelligence, deep learning. And this is why I think this is an important thing for us to learn about in the future, even though the second part of this has not been ratified yet, and it's an active discussion. So, pre-warning, some of this is going to change. And naturally, as the chair and leading many of these things, I can say with unquestionable honesty that many of the slides I have comes from the contribution of many other people in many, many different groups. So I have to give them all the credit for any errors that still remain. Okay? All the good stuff remain all mine. Just kidding. All the credits for all the errors and stupid mistakes are truly mine. The usual legal disclaimer comes about, and of course I want to thank all the sponsors. Interestingly enough, I don't know if they're on here. Oh, I don't know if they are though. Okay. As part of SG14, we just had a telecon 2 days ago, and in fact we were talking about using Conan and JFrog as a potential SG14 repository. So maybe that helps or not. But okay, so first of all, I'm going to take a look at C++17, as I said, and we're going to take a look at the road towards heterogeneous computing and how executors in ISO C++ is going to enable that. And then if I have time, I don't know if I will, but we'll talk about an existing language now that already enables heterogeneous computing, and it's called SYCL. Right. So this is actually not my slide. This is actually a slide from the itCppCon17 website. You can go there right now and grab it. I grabbed it last night because usually what I do is if I'm giving an overview, I really wanted everyone to have an idea where we stand right now. So this is a pretty good way of looking at where C++ stands today in terms of all the different features. What's happening, as in my experience as part of the committee for the last 15 years, and some of you guys are committee members here as well too, is that the Evolutional Working Group, which used to be the group charged with designing the language, has now essentially split off into multiple study groups. The study groups are essentially evolution working groups themselves. And it's hard to say whether these study groups are small or major, because they are actually tasked with designing the major features of the language. Whereas the actual evolution working group is now mostly charged with fixing the language itself, injecting C++ specific features itself. Okay? So as a result, we have a large number of working groups going. Now, this was actually predated to some extent even in C++11. Even in C++11, we had certain working groups going. There were far fewer, of course. There was the decimal floating point technical report that was not merged into C++. There was the library TR2, which was a kind of a separate group. That was mostly merged in. And then there was also a special math IS group. Okay? That generated things like Bessel functions and Fourier transforms, very specialized astronomical and physical functions, mathematical functions. At that time, it was deemed not ready yet for prime time, partly because the cost of building something like that from an implementer point of view would have been enormous. They usually use iterative methods, long computations for very high precisions, usually requiring an army of PhDs. So at that time, we weren't able to incorporate that in C++11. Now that came up again in C++17. Now, but before I get to that, you notice that we have, after after C++11 came out, we have C++14, and then, which was kind of a minor bug fix release because we found out after C++11 was ratified, we were actually missing some fingers and toes, you know, like C began, C end, little things that was kind of important. We fixed most of that. We added things like polymorphic lambdas and move capture, you know, fun things like that. And then beyond that, but they weren't major things. Beyond that, we started looking at towards C++17, and the hope there was that C++17 was going to be a major release, going together with something like the TikTok of Intel. You have a minor release, then a major release, and a minor release. So as a result, all these SGs spun out, and they actually, so you'll see that here, all the green boxes are where the SGs are. And the dark green boxes, including the math IS, the file system, the library fundamentals, and parallelism TS were all incorporated into C++17. The light green boxes are the ones that didn't get incorporated. And if they don't have a definite endpoint here like this, then that means that they weren't even published. Okay? If they have a definite solid endpoint, then they were published. So that little dotted line is kind of where we were after the March, the last meeting in Kona, March. And you see that we have things like concepts, transactional memory, concurrency TS1 published. Even library fundamentals 2 was published. Okay? But for many reasons, which I'll go over, they were not incorporated in C++17. And that is where the question lies. Why? And why not? What were we thinking? What were we smoking? And can I have some of it? There were other things that were ongoing, and rightly they were not incorporated. Things like networking, you can see that we were still processing it, parallelism 2, ranges, modules, coroutine, concurrency 2, 2D graphics. I hope this gives you, this one slide explaining it will help give you some idea of where all these things sit. If you have questions, by the way, please feel free to ask. I don't care whether, for this kind of talk, it doesn't matter whether I field them all at the end or in the middle of the talk. So we already talked about the pre-C++11 projects. Just for completeness sake, there was the technical report on C++ performance. There was the technical report on C++ library extension, which was mostly based on the Boost libraries. And most of it, 13 out of 14 of those, were injected into C++11. I think the only one that wasn't injected, was separated out, in fact, was the math special math functions. The math functions you'll see, indeed, I put red in here for yes, are indeed injected now into C++17. Even that was without drama. For a while there was a meeting about, I think it was in Lenexa, where there was a vote on adding it, and it was voted down. After that meeting, the group that was interested in it came back and told us, well, you know what, there's a lot of implementations now. Boost actually has most of the special math implement it. The implementation quality was high. So there was no reason at that point to really exclude it out. And to be honest, what was called special math back in, I don't know, 2002 or 2005 is now pretty ordinary math now. Even a lot of industries now actually use it in day-to-day research. So I think that was a good reason why we added that. And then, of course, the decimal floating point was something that was born out of the need to potentially support hardware that had decimal base 10 arithmetic as opposed to base 2. Okay? And this was not added to C++17. Now it's going through SG6, which is numerics. And in fact, one of the authors is sitting right here in the front. So I'm going to defer everything to him on this particular question. But the point is that it is being worked through as another addition to the C++ language, with obviously not 17, most likely 20. All right, now let's get to the biggies. File system TS was added. This was something that had long history in Boost. It allows you to essentially abstract out the difference between Unix, whether it's / or backward slash, the way you differentiate directories, and as a uniform way of moving in and out of directories. In fact, this is probably one of the first technical specifications that was added. The C++ extensions to Parallelism was something that I've always asked for right after we enabled threads. So one of the biggest things we did for C++11 was enable a thread-based model of programming. But we pretty much stopped there because that was pretty low-level stuff. One other thing immediately after C++11 ratified was I asked was, can we have at least parallelism in the standard template library? Well, we can't have it everywhere. We can do it at least in selective algorithms, and indeed that's what we have right now today. Now, this is in C++17, and it's widely implemented, but you hear that a lot, but don't get fooled there. It's widely implemented, but in various shades of gray. I don't think almost anybody implements it actually fully. Okay? We have implemented most of it, or all of it actually. That's my company. But I think its pedigree was actually based on things that were based on GPUs. It's things like Thrust from Nvidia, things like Bolt from AMD, to some extent Silk. So many of these languages predate this design, and they implemented essentially some or all or parts of these things. At the very last minute, we got cold feet. We added everything about parallelism that was suggested, except at the last moment, we had this messiness with how exception was handled. The way exception was going to be handled in the original design, and it's still in the Parallelism TS, was that we were going to create an exception list of exception pointers. Okay? And every time a single thread finds an exception, it was going to generate this exception pointer, attach it to this vector of exception list, this vector of pointers, essentially. Now, you can imagine that this is probably an okay idea if you only have a few threads running, but I think you can agree that if you have more than 500 or 1,000 threads running and they all start generating these exceptions, it's going to be a bit of a problem, especially if you have nested parallelism. Okay? So at the very last moment, we pulled it out. What did we replace it with? We replaced it with, essentially, it's going to terminate if even one exception comes out, and it's not even going to bother unwinding. Okay? Now, before you think this is a bad idea, many people who are experts in parallelism and concurrency believes that this is, at the minimum, what you should be able to get. And it's not that, and to be honest, it's not that hard. The reason this is okay is because now you can replace it with a better mechanism that can give you honest exceptions. Okay? This is a direction that we often do. So the next one is transactional memory. I'm the chair of the SG5 transactional memory. It gives you a composable log-free programming that we think scales better than locks or other things. We didn't put it in, we didn't ask for it to be put into C++17. Because at that time, we didn't think we have enough usage experience yet. It is in GCC version 6. Pretty much the same design as what we put in, just the keywords were changed for the sake of the innocent. But we didn't think that there was enough industry experience to come back. Part of the reason for that is there are actually two keywords in that design. One is called synchronize, which is really essentially just a composable, elidable lock, okay? That scales, but it doesn't do any rollback. The other one is called the atomic transaction, and that does true rollback. Now the second one is much more complicated, and this whole thing is actually just a software design. It doesn't require any hardware, okay? So the composable lock, the synchronized block, is a pretty good idea because it allows you to take a basic lock guard or any kind of lock, and it won't deadlock with each other, okay? Because it has intelligence to be able to cut short and serialize into a single global lock. But the thing is that we didn't do any, with that particular feature, we didn't do any, enable any particular rollback capability, which is normally what you associate with transactional memory. So we were divided in terms of trying to decide whether we should put forward just that one feature for C++ standardization, or put forward both features. And until we have usage experience, we can't make that decision. Okay. The next one is the library fundamentals. It adds amazing value, things like optional, any, string view, and a lot more. And it is of course incorporated in C++17. And then finally, concepts. What can I say about concepts? So concepts was published in late 2015 and is now being eyed into merging for C++20. And it failed, interestingly enough, the test for being included in the C++17. That meeting was one of the most controversial I've ever attended. The discussion for that essentially started at something like 2 or 1:30 in the afternoon and lasted till about 6:30 in the evening. Not all of it were concepts, but certainly a large part of it had to do with that. It is not true that after it was refused to be, or voted down to be added to C++17, it is not true that Beyond swore in English. I think he actually swore in Danish. So what's going on there with concepts? I wanted to talk a little bit more in detail about that because, I have to do this. Because it has a fair bit of back history about it. Now, before there was obviously the original concepts. That was a very large design that enabled things like prototype, template argument prototype checking, and also it included what's called separate checking. The fundamental idea of concepts is that it solves probably one of the first key problems of C++, and that's called the error null problem. This is the case where if you have some template instantiations, it instantiates other things. Eventually, it finds that it doesn't have any clients, that it has the functions that it needs. And as a result, it cascades into this giant novel. And you start reading this novel backwards, from the bottom up, until you get tired, or until you figure out the problem. Okay? It turns out that smart people looked at that and said, well, the best way to solve that problem is create essentially a prototyping check on the template arguments themselves. And having that capability allows you essentially to early shortcut the error almost right away by saying this template arguments require the ++ operator or something that is copy comparable, something like that. And when it checks the client and it doesn't supply that particular function, then it can now shortcut that error message right away, shortcut that novel right away and say, you don't have this particular function capability, and therefore essentially give you a shorter novel to read. That's where the story starts. Unfortunately, as it keeps going, we realize that before C++11, much of the complexity of that is that having all of that plus something else called late checking infects essentially even the simplest operations. Even if you wanted to do just stream output, you would have to understand concepts. And that was considered an untenable way to move forward with concepts back in C++11 days. With that, we figured we injected something in C++17 now for the concept study group, something called Concept Lite, that essentially just does the prototype checking aspect of it, but not the late checking. Okay? And what happens there is that we realized that this essentially allows us to get most of the errors, but not all. Because fundamentally the goal was to be able to trap almost all the errors. And doing this late definition checking is something that was debated back and forth in the committee when we were trying to decide whether to add it to C++17. What was happening was people was hoping that we could still add some amount of this definition checking the actual definition of the template itself. And some people wanted to make sure that the design enabled that. No one was able to give that fundamental assurance. Okay. And because of that uncertainty, some people wanted to wait. Some people wanted to wait so that we were sure that we can get some sort of late definition checking. If we have definition checking with this template prototype capability, then we would truly potentially reach a stage where we can catch errors purely at the call site or purely at the definition site. Something that Haskell and Russ, and I know some of you guys are here because I talked to some of you guys last night at the speakers dinner, something that Haskell and Russ already can do. Without definition checking, it's unlikely C++ will ever be able to fully find all the errors at the definition site. Okay. And this is fundamentally the dichotomy that the committee is trying to figure out. And because of that, we decided to not put concepts into C++17. Was that a right decision or not a right decision? Only time will tell. Okay. At this stage, I would say that forget about definition checking. Indeed, in the words of one of the committee members, is that we should just throw it under the bus. Because it doesn't seem clear either way that this is holding back something as important as concept, which probably will give you essentially, I don't know, 75% of the errors that you might get otherwise. Okay? Holding that back for 100% of all the errors, including the definition errors, is probably not worth it. The danger of where that goes is, with the current design, we might never get to full definition checking. Okay? I don't know that for a fact because I am not a concept expert, but this is indeed some of the issues that the group was essentially fighting with. The next set has to do with concurrency, library fundamentals 2, the ranges TS, the networking TS, and the modules TS. And what these are is that the ranges TS, and these things have significant changes to them. So the concurrency TS was another TS that was ready well before C++17. And it enables interesting fun features like features. A new different kind of features. You see, the current features that we have that comes out of std async blocks. You have to wait and you have to go get the future back. For an asynchronous functionality, this is not particularly desirable. And indeed, some people would claim that async is kind of broken. The designers didn't feel that way. Async was never meant to be that kind of asynchronous capability. It was really meant as just a thread replacement. And they do block. Okay? So we wanted something that didn't block, that was async-like, a feature that did not block, and that's what's going to be in concurrency TS. Because when we get that, we can now compose them with other kinds of features, so that when any feature comes back, or when all the features come back, you can now select the result. That chaining is only possible if they don't block, right? Because if they block, you got to stop and come out of your composed equation and get the value and then inject it back again. This essentially, with this capability, it creates what's called a dot-then continuation. Now you can have a chain of features that essentially continues from one after the other. A desirable feature, implemented, because Microsoft essentially already has all of it happening. They are one of the two implementations I know of, although of course in Microsoft it was all part of C#, so it's not exactly the way we have it. The other reasonably complete implementation I know of is Anthony Williams' Just Threads, which works for x86, I think at least, but you have to pay for it. He hasn't found a huge amount of uptakes on that, but it is there. There are a couple of other things on the concurrency TS, that's for latches and barriers and atomic smart pointers. So these were ready, but they weren't ready enough in terms of for C++17 because I think its ratification date is 2016-01-19, January. And the decision point for that, for C++17, was in February. Okay? So we just didn't feel big, and because this is not exactly the Microsoft implementation, and at that time Anthony William hadn't completed his, having it been out a month, we just didn't feel like it was ready enough. The next one, the Library Fundamental version 2. Library Fundamental 1 is already injected from the previous slide. Library Fundamental 2 just adds on to that, gives you source code information, capture, and various utility. In this last meeting, March 30th, that was published, is fully published. So obviously, it didn't make C++7 because it actually came in after we were picking stuff off of it. The ranges TS. So all the red stuff I wanted to mention is what's new that came out of this meeting. Because I show these slides a lot, and it's actually on my website. And every meeting I update these slides. So I always want to just turn red something that is significant in terms of what's new. So ranges TS. This gives you range-based algorithms at these. It's essentially tagged as potentially a replacement for iterators. This one is being sent out as what's called a preliminary draft technical specification. That's what PDTS stands for. That's just the one step just before full ratification as a technical specification, not as an IS, an international standard. Okay. The ballot has since come back, and the library group is busy addressing these things. Then there's going to be a few changes with the working draft being to the working draft before it's being approved. The focus at this meeting, obviously this last meeting, was that the C++17's committee comments had to be addressed. So not a lot of time was able to be spent on the ranges TS. So it's not going to be ready for final publication probably even until the next meeting or even the one afterwards. The networking TS gives you the ability to do things like URLs and sockets and post and defer execution of functions to these URL sockets. This was also sent out for PDTS, the step just before the IS. The library group didn't actually have any time at all to spend on addressing the comments that came back prior to the meeting. So, because again, C++17 was the focus, so we didn't get to it. Modules. I know many of you guys are looking to find out the status of modules. So right now, there are two implementations, one from Microsoft and one in Clang, which diverge in some aspects in their conceptual and implementation model. The real issue with modules, let me just outline what modules is. This solves essentially what's called the second major problem with C++. This is called the constant recompilation problem. This is where if you change some header file and it's deeply nested included by other header files, you're going to get this rebuild, which is going to on pretty much your entire project file. People have tried to solve that in the past with things like incremental compilation, just compiling the ASC tree of the part that's changed. I worked on that for much of my life. Okay, but it was just those ideas fundamentally were unsatisfactory. Whether you do it from a compiler point of view or using dependency project makes and things like that, okay, it still was complicated. So they were all trying to solve one thing, essentially. That part of that one thing, and there are other things though, is to shorten the build time of C++. You ever had that where you make some changes and essentially you go away for a while and wait for it? This is the time when you can pretty much do anything, and you can tell your boss, oh, well, it's compiling. It's the universal excuse for pretty much anything that can happen. I know I used it. That can pretty much buy you at least half an hour to an hour of time. And the way module does it is that it's based on a previous idea. Ever heard of precompile headers? This was a Microsoft thing where if they noticed that every Microsoft header file, because it's Microsoft, they always have to include windows.h. Okay. And windows.h doesn't change, really. So they would precompile essentially everything that was in windows.h and many things after if you didn't change those, and keep it as a binary pass-through. And before they build the rest of your file, they would just inject all the changes, all the binary code representation that was in windows.h. Okay? This significantly improves your build time. Modules would do the same thing, except now you would control it. You would use keywords like import or export, okay, to import a particular module file as is. Okay? The problem comes as they worked on the design comes in one area particularly, and it had to do with macros. And the problem there is pretty obvious, pretty easy to understand. Macros changes the compilation path of your code flow. Okay? Depending on what the macro setting is, it could compile one part or another part. And that really messes up macros. I mean, sorry, that really messes up the modules, the import and the export aspects of it. And indeed, this is exactly the point that the divergence between Clang and Microsoft. Microsoft chose not to deal with macros, okay? Partly because they feel that modules isn't really for legacy code. New code, and because one of the directions of the committee eventually is that we're going to do away with macros and preprocessors completely. I know some people gasp when they hear that, but it's true. Okay? And some people smile at that because, oh my God, thank you, finally, we don't have to deal with preprocessors or macros anymore. Microsoft felt that that was really important. And so they did not put macros, handling of macros, in their module implementation. Now they did take account of using a side file, okay? But that actually will significantly bring back this build time that you were trying to solve. Clang tried to take advantage, try to consider macros, and this is indeed where they design. This is where they diverge. And with modules, it was because of this separation, people were trying to decide what do we do with this design. Finally, at some point, there was an agreement that we would essentially base the design on the Microsoft implementation. And much of this TS is based on that implementation. However, in the last meeting, Clang came back, the Clang people came back and wrote their experience report for implementing modules. Even though theirs was slightly different than what the design setting was going to do, they actually do a little more. They try to take account of macros. Their experience indicated there was some significant concerns. Okay? And one of the concerns of the discussion was the name lookup issue. Okay? I don't want to go too deeply into it, but this name lookup issue, that would come up during, it came up during wording review of the module TS in core. And it involves a case where you have a bunch, some module A and some module B, some template, some non-modular legacy header code, functions that was exposed in one part and unable to be visible in another part unless you imported the right set of modules. Okay? And it turns out that as typical with these cases, you're going to get issues with either ODR violation or compiler error, or you might have a different definition being picked up. Serious problems in C++ that makes it very difficult for people to figure out where the solution is. If you kept the pound include system, none of this would occur. And this was a big enough problem that they felt both sides argue, is this a serious enough problem that people actually encounter? The Microsoft group said that they never saw this problem before. Clang people said they saw it in tons of their code. Who do we believe as a committee? So at this point, it was decided that we would continue with the current syntax, okay? And it was hoped that with V1, that's why modules essentially did not make as a PDTS. It had all the chance of making it, but this particular issue kind of sidestepped it. And it was decided that we would take some more time to look at this issue to see if indeed people were normally experience these kinds of inclusion problems. Next one. Okay, the next group highlights the last few sets of working groups that we have. The coroutine TS. Are people here familiar with coroutines? Good, good. Just to give you some basic introductions about coroutine. Coroutine is nothing more than the generalized functions that can enter, resume, and suspend at any point. The difference is that a generalized function generally can only enter at the top, exit at the bottom. except there's a few points in between you might throw an exception that could make you exit as well too. But in a generalized coroutine, you could enter and suspend the function, go to a different stack, execute a different function, resume it back to the original function. This is extremely important in things like Duff's devices, where you don't cause things, where the normal function requirements causes code inversion. Now, when coroutine was offered, it was originally offered by Linden Labs, the people who brought you your Second Life. Okay? They obviously know a lot about concurrencies, and they use coroutines a lot in their code. They brought in the they came and asked us, if you guys have coroutines, would you want it as a language feature or a library feature? And we came back, as usual, as a committee, says, oh, it should be a library, because a library involves the fewest changes in the language. So they came back with a library approach, and that was examined, and when we examined it, it turns out that there were some thoughts, and indeed I'm guilty of that because I actually brought up the issue of performance at one point. And they thought, well, it's not going to be the most performing, because what it does is because it's a library, it's going to have to use the stack to switch over every time you suspend and resume. Okay. So someone else, Microsoft, came back and said, well, we have a faster implementation. It's actually based on something like fibers. And it doesn't use the stack, it uses the heap. Okay? Hence, it's called the stackless approach. The library approach from that point on was called the stackful approach. Okay? But I always think of it as the language approach, which uses keywords in the language, manipulates the heap as the stackless one. It doesn't use the stack to do function switching. Whereas the library approach uses the stack itself, because it's the only thing it can access if you're a library. The Microsoft group pushed their proposal significantly, and it actually advanced very quickly. And indeed, that's what most of coroutine is. And it's another one that actually succeeded in the last meeting to go out into as a preliminary draft technical specification, a PDTS. And it's solely based on the Microsoft approach, solely based on stackless, fast switching using the heap. It turns out that there are things that you might not be able to do with the stackless approach. Okay? And the committee obviously wants everything that it can get. So it wants things like, so it actually implored the library implementers of coroutines to come up with their approach and try to bring that into the coroutine TS. And that probably might happen. I think the library people, the people from Linden Lab, still want their library approach to be considered as part of the TS. There's another group that is also trying to unify the library and the stackless approach. And there's this so-called unified proposal that is in flight. But after the last discussion, I think it's clear that having this unification is only going to make things much bigger and give you really no additional benefits. So I think we're going to abandon that at this point. So I think the result is that coroutine will be there will be the Microsoft stackless version in the TS right now, and later on we will either add the library version using either the same TS or an additional TS. Now it's clear that since this is now going out to PDTS, it will probably be added to coroutine version 2. Okay? Because they can't really change this TS with a huge injection of a brand new feature at that point. The reflection group approved, so the rest of these are less confirmed. They're obviously all work in progress. The reflection group essentially confirmed a static introspection proposal. I think other than modules, concepts, reflection is one that I hear a lot of requests on from many, many different fields. It turns out that the ability to introspect, to examine and say whether you're a class or a class member or you have virtual functions is something that everybody needs to have. You have it in some respect, but it's a runtime reflection. Things like RTTI, dynamic, type ID, these are executed at runtime with massive costs in terms of the amount of the code size that the compiler has to generate. If in order to identify a type ID, and I used to be a compiler implementer when I was with IBM on the Excel compiler, you pretty much have to duplicate the entire virtual function table and every possible transfer point. Okay? That's not great. If you can have it as a static compile time only capability, you would reduce the compiler magic down to maybe 1/10 of what it is now. Okay. Some things the compilers still have to be, you still need the compiler to be able to tell you. Other things, essentially, is just based on metaprogramming template magic. Okay. The contracts. Contracts programming is another one that is still work in progress. The proposal at this point passed core language design review, similar to the reflection TS. Contracts is something that is extremely important if you care about safety or critical safety aspects. I think this is something we're going to all start caring about in the Internet of Things and in terms of self-driving cars. If C++ has a chance to be used in these growing fields, it needs to be verified to be safe, okay, in two aspects. One, functional safety, the fact that the system does not give you ambiguities or undefined behaviors at the undesirable times. It does now. And two, process safety, that it has to pass ISO 26262 safety certification. What contract does is it gives you the beginning of that, because what it means is that what it makes you, the programmer, do is promise these preconditions before you enter a function, or post conditions that has to be verified and checked. Okay. And because of that, it gives you the beginning of safety critical support. The next one is executors, and this is why I come mostly to talk to you about in the next half hour. Executors, in case you're wondering what it's all about, I'm going to tell you in the next half hour, so I'm not going to go into too much detail, but it is essentially a way for people to control the execution of functions. Up till now, you have capabilities like async, you have capabilities like parallel invoke, okay? Their capabilities allows you to spin up lots of threads, send off executions asynchronously, or create a group of threads and have them do your task. But at no point in those keywords do they tell you how they're going to do it, where they're going to do it. Am I going to do it on SIMD? Am I going to do it on the GPU? Am I going to do it on the CPU? Or when they do it. This conflation, right now they only give you one way. They use std thread to do their things. They execute it on CPUs. Okay? And other than async, which gives you a defer or immediate separation of capability, they're pretty much anytime std thread could be executed at any time after you issue a command, you don't know. Okay? So you lose all of those control aspects of it. What executors give you is that control back. Now I'm going to talk about that. What it does give you, because now it enables you to say where things are to be executed. Implicitly, that means now you have ability to bring executors towards executing on heterogeneous devices. GPUs, accelerators, FPGAs. And that's what I'm interested in. This is not an official TS yet, but I'm working towards these, and this is where my major interest lies. So the summary is C++17. It is on track for final publication by the end of 2017. It's got things like file system TS. It's got things like parallelism TS, library fundamental TS, if-const expr, and various other enhancements. And it is out for publication. We thought it was going to be able to make Toronto, the meeting that's coming up in about a month. That's my hometown. And it isn't. The ratification won't make it. We thought it was going to do it. That's why we delayed the meeting from between the last meeting to the Toronto meeting about 4 months. It turns out that there's some translation aspects that now needs to be done, and those took a lot of time. So I didn't even see the ballot until last week. And that ballot's going to take another 6 months for that to go. So I think it's still going to have the potential of finishing by C++17 by 2017, but now I'm beginning to be dubious. I think it's going to be tight. C++17 might be 2018. You heard it here first. Okay, I'm not going to go through the rest of these slides. I've been maintaining this as we go along. All the features of C++17 in terms of language features that were voted in There are some key ones here that's important to identify. Things that are trigraphs been removed, folding expressions, things that I've essentially put in, or lambda capture of star disk by value. Those are key features to pick up. Previously, you couldn't capture the disk pointer by value. You had to capture it by reference because it's a star disk. If you pick it up, it's going to be a reference. Okay? And because it's a reference, all the members of pointer had to be captured by value. And you couldn't control it any other way. Now you can. I've given talks about that as well too. C++17 language features. Two things that we never got that people wanted was default comparisons and operator dot. Okay, for 17. There were lots of library features voted in. I'm not going to go through them all again but I think std variant is significant to identify. So if you look at the number of pages, you'll notice that C++ is growing by leaps and bounds. Used to be in C++ 98, 800 pages. 17 is probably going to be well over 1,500 pages. It's going to double. That's not so surprising because lots of other languages are doubling as well too in terms of sizes. Okay, you know, but not as much, and you might think C++ is getting more complicated than any other language, but by degree it might be. But in terms of comparison, they all are increasing in their complexity if they have any kind of lifetime at all. It's, in my opinion, having been in the C++ standard committee for some time, it's quite stable. Okay. C++11, the committee draft, had 500 errors, and then the disk had another 500 errors. 14, because it's a much smaller version, had only about 100. Whereas 17, it's not a small release, but it's not a huge one later on, you'll see by my conclusion, had about 400 comments coming back. In terms of spread across countries, you know that as usual, the US had a great deal of them, followed by all the various different countries, between Spain, Great Britain, Russia, Japan, Canada, Finland, Switzerland. There was a bunch of significant late comments. If you were to look at by committee, you'll see that the library evolution group, had by proportion the largest number, followed by the library working group, the evolution working group, and the core working group, and then finally the concurrency parallelism group in SG1. So after the committee draft came out before the itCppCon meeting in November, people were looking at the two meetings after that, one in itCppCon and the last one in Kona, to see if we would put things back, because people really wanted it. Well, we didn't. We didn't put concepts back. We did not put unified call syntax back. We did not put default comparison back. We did not put operator dot back. We asked right at the beginning of the meeting whether there was enough stomach to talk about these things, and the consensus was there was not enough stomach to talk about it. One group actually asked if they could pull out inline variables. That stayed, because again, the committee essentially operate by consensus, and every item is measured in terms of whether it's going to increase consensus or decrease consensus. And if the answer is that if you pull out inline variable, it's going to decrease consensus, the status quo remains. In Kona and itCppCon, we did do a few things. Finally we removed the exception specification. It was deprecated, okay, in C++11. It's now finally gone, okay. This is the thing that you can add, the throw statements that you can add to the end of your function as a contract to kind of promise what's going to come out. It turns out that much of it was essentially useless, okay. We added elementary string conversions, and std byte was added in the last meeting. It had a bit of controversy. Seems like nothing happens without controversies, but in the previous meeting, it wasn't even suggested as part of the feature for C++17. Then Canada, my group, asked for the feature to be put in, except to change the name. That turned out to be, the last part turned out to be controversial. And so, if there was any controversy at all, as I said, decreasing consensus, we dropped the whole ball in itCppCon. In Kona, we just came back and said, can we just get the feature back, but use exactly the same name as std byte that was suggested? And they said yes, and so that's what was added. I keep a list of these, like I said, I keep a list of these features in my website, which you can find fairly easily. But you can also go to this SD6 recommendation page, and it will keep a list of the features as feature test macros. What it means is that these are macros that test to whether a feature exists or not in your compiler. So it's a pretty cool way of being able to tell you what features are being actually in C++17. Okay? We have already started adding C++20 features. There was an overall direction plan moving towards C++20 to have concepts, modules, ranges, and networking at the very least. It doesn't mean it excludes things like coroutines and contracts and transactional memory. It just means we don't have an infinite resource, and if we have to prioritize the work, these guys get more the priority. Actual features themselves, we have already started adding things like pack expansions and using declarations. We started lifting restrictions on required expressions and a whole bunch of other things. I'm not going to go through them. This list will slowly grow, and I'm going to keep up to date, as with many other people. Okay. The future C++ standards in Kona, we essentially address all the remaining comments. And once we address them, we issue what's called a draft international standard. That's in the standard language, that's almost one step before the final international standard. And the idea is, if you're concerned, the idea is that if there are no comments on this draft international standard, it becomes the international standard. And given the fact that people have actively participated, we don't expect there to be any kind of additional comments. So it's a pure up-down vote, either yes or no. It turns out, as I said, it's not going to be approved, ratified. It's essentially approved, so this is why I'm confident to give you this report card. But it won't be fully ratified by Geneva. Those people take a fair bit of time. So after C++17, we continue on a 3-year cycle. And then the C++20 prediction it's a massive train. Yeah, I know, I heard that also. Concepts, ranges, concurrency, TS1 and 2, parallelism, TS2, executors, which is now a separate TS, not part of concurrency as it had been meant to be. Reflections, coroutine, networking, modules, transactional memory or some part of it, numerics, and maybe heterogeneous computing. The report card, finally. This is actually not my report card. Before C++17 in 2015, Biana wrote a paper, you can find it, that says these are the things I would like to be in C++17. So I pulled it out for my talk and scored them and looked at them and noticed that he says he wanted modules, he wanted contracts. Well, he's not getting it. We did get a type-safe union. In terms of supporting higher level concurrency, we got a score of 1 out of 6. The only thing we got was parallel algorithms. We did not get networking, SIMD, futures, improved futures actually, coroutine or transactional memory. In terms of simplifying core feature use and addressing major concerns, we got 2 out of 8. Okay. There was some hope that we would revive default comparisons and operator dot. They turned out not to be true. There were rumors. The only thing we got was array view, string view, and optional. So the verdict on C++17 from 2 sides. We blew it. It was not a major release. You didn't take any risk. Therefore, you're not going to get anywhere. People were concerned that we were not implementing TSs, that these TSs are now beginning to follow on each other, and they're depending on each other. Like ranges cannot go in until concepts goes in. Okay? And this bus train model that we're using, sometimes you miss the bus. And that's the fact of it. The other side says we did a nice job. It's not a minor release. It's safe and conservative because C++ has so many users, you can't radically change it. The TSs are actually being implemented. There's some truth and some falsehood to that. And that we should keep following the rules of a bus train model. And this is how you can get 110 people to get working together. So my verdict, it's a medium, it's an okay release. It's not great, it's not bad. It will give you something. Probably the most significant thing, in my opinion, it's going to give you is a speed up in terms of parallel algorithms. This is something that you can add using additional arguments to the parallel algorithms like sort or transform or reduce. That essentially will give you a speed up if it's available. Okay. I think that is noticeable. There are other things like optional and variant that will make your life a little easier. Okay? So that essentially gives you my report card. I've taken a bit more time than necessary, so I'm going to hit executors in ISO right away, unless there are questions. Okay, thank you. All right, so let's see what executors sits. This is probably the first public presentation of executors ever. Okay. Essentially, in C++ today, there are these planets that orbit the sun that deals with parallelism and concurrency. There's SG1 that deals with parallelism and concurrency, thread-based model, memory models. There's SG5, transactional memory, and SG14 with low latency. And it turns out that these guys essentially add all the features that add parallelism and concurrency to C++. The red stuff is what's already in C++17. The blue stuff is the stuff that we're still working on and coming. So right now, out of this group, Parallelism has parallel algorithms, and we've started adding forward progress guarantees. But we plan to, in future, and indeed, these are what's in Parallelism TS1. Parallelism TS2 will add things like SIMD vectors, task-based parallelism, execution agent. Concurrency originally was going to add things like futures plus plus. This is that non-blocking future. There's resumable functions, lock-free techniques. It was going to add executors, but in the last meeting, we decided to pull executors out into a separate TS. And the reason is we feel that it's the one TS that binds all these other things. And increasingly, as I work in it, I feel that it's one of the biggest features in C++ that's going to end up binding almost everything in C++. This is not a bad thing because it gives uniformity to it, and I'll explain why. But we're going to have other things in concurrency TS, but as you can see, none of it is actually in C++17. So what is executors? Executors essentially is the glue, very similar to what iterators do, gluing between algorithms and containers. So you can switch between different algorithms and different containers. Okay. It turned out to be magical for C++, having this idea of an iterator concept. The same thing is going to happen for executors. If you have all these control constructs that gives you parallelism or concurrency, there's async, there's for each, there's defer, there's task blocks, and you have all these places to potentially execute them, it turns out that if you don't have this middle unifying piece that binds them into a end-to-end relationship, you're going to have n times n control structures executing for every single possible devices or SIMD that you might have. And that's not a desirable place to be at. So there's been a number of proposals from Nvidia, from Google, from NASDAQ, from Codeplay, because we work with executors all the time. We dispatch for low latency reasons, NASDAQ. We, meaning my company, dispatch the GPUs. Nvidia doesn't care about the dispatch as much, but once it goes to a GPU, it has to be executed in bulk, meaning it has to fire off millions of agents. Okay? Google has routinely dispatches in a simple manner for execution anytime you have a query on the internet, for instance. So what are executors? Well, you have all these resources. There might be, it might be right now an OpenMP resource, an OpenCL resource, a CUDA resource, or pure C++ threads. And you have all these asynchronous capabilities, all these control constructs that allow you to access it. And what executor does is that it will give you this unified interface. Now here's a simple SAC speed calculation. Those of you guys in, who publish papers in numerical physics will know what SAC speed means. It means the sum of AX plus Y. Okay? It's a basic equation that essentially people use a lot to test performance because it pretty much does have most of the things you need to do. So if you were in OpenMP, you would have to invoke a parallel region and do your AX plus Y. X plus Y in this case are vectors, by the way. If you were in a C++11 thread, you would have to use a lambda expressions and send it to a std thread execution. Okay? And essentially would do the same thing. This is pretty cool. That's why C++11 threads is pretty cool, because it gives you this familiar interface way of doing computation. If you were using in CUDA, you would have to identify the block address ID, the dimension of that, and you would issue a similar instruction. SYCL, which is a Chronos C++ heterogeneous language, does exactly the same thing, uses pure standard C++ template. And it uses the same instruction, but now you have to issue a library function that indicates that it is now going to a GPU. In the future, with executors, we hope you can just write this. Create your own executors, which you will define earlier. You will create a bulk execution. This one is sending to for instance, an Nvidia GPU, where it's going to dispatch millions of threads to do this execution. You would describe the shape of the computation area, in this case, only a one-dimensional shape. And you would have an index that would be used to compute AX plus Y. Okay? This one could be sent to a GPU, to an FPGA, to an accelerator, or to a CPU if you don't have any of those. It could be sent to your self-driving car. Okay? So the purpose one of executor is how execution is done. Because right now, this is how you do a for each in the parallelism TS in C++17. It says, I'm going to execute it in parallel from the beginning to end. Yes, we still have the old iterators. This particular lambda function. But it doesn't allow you to say where to execute it. Okay? It's going to be on the CPU, and that's it. It doesn't allow you to do it on the SIMD. It doesn't allow you to do it on an OpenMP device or a GPU. And it doesn't tell you at all how it's going to be executed. So we know that programmers want to control the placement. So you could do it like this. Okay? If you can now essentially tag on the paw and say, I want to do this on this particular executor. Next part is the second purpose of executor is control the relationship with the calling thread. Okay? Here, if you have async today, you have some launch flag which says either defer or immediate, and that's it. Okay? There's no relationship there with the calling thread. How many threads do I launch? Where do I launch it? How spread out is it? Is it going to be spread tightly bound to the original calling thread for cache efficiency? Or is it going to spread out evenly across all the different cores that you have? Okay. In the future, by changing that launch flag to executors, we hope we will be able to do that. The third purpose of executor, and this is the scary one, is this is the one that's going to affect everything. Because it wishes to be the uniform interface for scheduling semantics and access control structures. So as such, you would use an executor wherever you have a for each, or an async, or future, or dispatch, or even a transactional memory. This is something I'm working on with a separate group. This ability to do things uniformly, to execute functions uniformly, is the part that's going to affect all your lives, eventually. Okay? Because everywhere you're going to have to figure out, what am I going to put here? What is going to be inside these executors? I will tell you in about 5 slides, I hope. But in the short term, we definitely want the executors to work with the C++17 features that we already know we have. Things like async, invoke, for each, and sort. But we also wanted to work with the technical specifications that are upcoming, that we are aware of. Things like task log, futures.den, things like networking, asynchronous operations, and transactional memory. Now, the problem is that with executors being so broad and trying to be needing so many people needing support for executors, it's gotten, certainly it's gotten the fear that everything is now lumped on top of it. You could, ask it to do remote execution, higher level variadic instructions, heterogeneity. You could ask it to do distributed computing. Essentially, it's an MPI killer. Okay, it could be an MPI killer, but this would really weigh down the whole design. So as a result, our group has specifically stated that these things are out of scope for our proposal. We are just going to try to get execution defined. How execution is going to be done in C++ for the foreseeable future defined. We're not going to define any of these other things. It is incredibly easy for anyone to add things, once executor is in place, to add things like thread pool, system resource, memory management, the ability to access near and far memory, the ability to spread out for affinity, all these other things that people want this to do. But we're not going to do it because we want you guys to do that when we're done. And the idea is that, so you'll probably right now still imagine, well, what is he talking about? What exactly are these executors? Okay. I know I've got about 10 minutes, so I'm trying to get through this. This diagram I found incredibly useful for when I was trying to figure it all out. And what it does is that it tells you that executors has one or more execute function, okay, where you actually tell it to do some execution, execute or dispatch. This execution function now, the job of this execution function is to create these lightweight execution agents which execute a stream of instructions. Okay? Now, that's the bottom part of this picture. At the top of the picture, you see that there's this binding thing that goes both ways. This context at the very top runs these agents, but also mediates. I think I used the word manage, actually. It manages the execution resource, the where you're going to execute it. Is it going to be on the GPU? And what the platform is of that execution. This is essentially what execution, what all these words is trying to say that I just essentially said. So you'll recall that here, this execute function is the key thing that you have to say in your code that I'm going to execute this. And it turns out that we think that there are at least three groupings of these execute functions. Yes, you can use the keyword execute, but we think that that is just the simplest idea. In a more complex way, you might have an async deferred execution or a bulk synchronous execution. Okay? And these essentially bifurcates into all the possibilities. So let me enumerate the possibility. Right now, the group believes that there are at least three ways that this possibility can break up. You can consider it in terms of cardinality, whether it's a single execute, whether you are dispatching a single execution or you're dispatching a bulk massive parallelism execution. Okay, so that's why you have either single or bulk. You have directionality. This is saying you can either have the execution be a fire and forget, and you don't care about the result that comes back, or it's a two-way where you care about either the value that comes back or the exception that comes back. So this particular type of execution creates a way to have a channel to feed back the results of or the error of the execution. The third cardinality inverts blocking. Whether something is going to be blocking or non-blocking is important to know. Now, if we chose not to enumerate every possibility, every type. So as a result, you'll see that the single execute creates a bunch of single post and defer. You'll notice immediately that post and defer seem similar because they have exactly all the same dimensions. The only difference is how tied they are to the calling thread. Okay. Async execute differs, obviously. Again, you have all the possibility, asynchronous execute, dead execute, and synchronous execution. And then bulk execute also essentially has many of the same points of design instantiated. They have the bulk case, one-way, two-way, and the blocking has either possibly blocked, or it doesn't block, or it always blocks. And the reason it's like this is if you have a generic template, you would pass in something that is possibly blocking, because at the point of definition of the primary template, you don't know whether the execution functions that people actually use is going to be blocking or non-blocking. So at that point, it's a possible block. But once you instantiate that primary template, you will know whether you're going to be using a for sure blocking execution or non-blocking execution. Now, we're trying to simplify this, but that's under discussion right now. Just to show you what execute says, execute is pretty simple. It just says run the function object immediately if the rules allow it. Otherwise, submit it for later execution. So, for example, you can have a thread pool. Post just says submit the function for later execution, but never run the function object immediately. Okay? Defer subtly implies a continuation relationship between the caller and the function object. Basically, wait till I'm done. Okay? I'm not going to go through these too much. I hope that you can look at the slides. So with this design, we hope that you can just look at the function name and know its characteristic. You know you'll notice that the function names have names that tells you that this essentially will synchronize, which means it's going to block. Okay? This will execute. This is a non-blocking, asynchronous execution. And at the very top is the execution. There are two tree structures here. One is the single agent. The other one is the bulk agents. Okay? And then there's a then continuation that allows you to chain executions together. It isn't quite as clean as we had hoped, and indeed there's now fervent wish to simplify even this particular structure so that you wouldn't have to worry about so many different ways. I do only about 4 or 5 minutes left. I want to get to what you would have to do. When you define an executor, you can do something like this. You have to create an executor class, and in the executor class, you have to define what is the execution category. And I went over those. Those are the 3 cardinalities. You'd have to tell me the shape type. You have to tell me what it's going to return. Okay? And once you have all these things, you can now say that this particular executor is going to call an bulk async execute. And that's how you define it. How would you use it? I want to show a final slide that uses a thread pool. Let me see if I can find a good one here. So this is defining how, actually I'm going to go back to this one. What this does is, here's in the context of a thread pool, you have created a pool of threads from which you're going to pull various threads out to do your task. You would create yourself an execute function, okay, and submit it, and you would define in the thread pool various contexts and operator functions, okay? And this is essentially how you would define your complete executor, okay? And that's basically all there is to it in terms of how you would execute. So this essentially shows you, as a summary, what execute does is that it decouples the control structure from the work itself. The goal we have is to compose with the existing control structures. What we have is what's called a minimal proposal, meaning we're not trying to do distributed computing or heterogeneous computing. And we're hoping that by doing it this way, we provide a foundation that we can build on. And through this method, we hope that this is essentially what's going to lead us towards the next part of C++, the ability to support heterogeneous computing. I'd like to end at this point. I do have more slides, but I want to stop here and take questions. Thank you very much.
Did you study any possible interaction between the executors proposal and the coroutine?
Good point. The question is, do we consider the executor proposal interacting with the coroutine proposal? And indeed we did. The executors can be further simplified with the coroutine, co-await, and co-assume. That's the new keywords right now. And it turns out that they significantly shortcut the then continuations part of the executor proposal. So it does work really nicely. In fact, Gore is an active participant of the group as well, too. So yes, we did. Thank you.
Hi. So I have a question related to FPGA. So you told that the executor can be also like deployed FPGA. Do you have any more information? Because I know FPGA, you just compile everything there, but when you are going to execute something, maybe you want something which can change during the execution. Okay, so the question is, I mentioned FPGA support for executors. Have I actually tried or considered the design of it? No. This is one of the hopes that we can support FPGA. I have to be honest here. I know FPGA is basically always going to be the elephant in the room. Anytime somebody says they can support all the heterogeneous devices, it's the easiest way to trip them up and say, how do you support the FPGA? And you just did that to me. There's a lot of heterogeneous languages out there that claim they support FPGA. Chronos has a whole bunch of languages like OpenCL, which says that they do support FPGA. And the problem is FPGA is so fundamentally different in terms of its execution model. It's basically a design on-the-fly compilation model. And it's the only one, I mean, OpenCL does work with FPGA because it is used by groups like Xilinx and Altera, which actually use OpenCL. And now they're beginning to use SYCL, which I didn't get a chance to talk about. But the only difference is SYCL is essentially the C++, native C++ form of OpenCL. Okay. Having C++ fundamentally support FPGA is still one of my goals. How do we get to it is something I still have no real idea on. So I can only be honest there. You got me.
More questions?
Hello. I have been teaching C++ at the university to very young students, and I see that the standards, the standard language is going to increase in complexity a lot. Is there a plan to reduce this kind of complexity in, like, for example, removing something has already been done, something deprecated has already been removed, but is there a plan to go on this?
So thank you for asking that. The question is, C++ is only getting more complex. Is there any plan to reduce the complexity? Let me just say what the official party line is, and what I think really is going to happen. The party line is that we are always trying to reduce complexity. One of the main goals that Beyond has stated is to make things easier for non-experts. And we try to do that every day. Sometimes, whether that increase or decrease complexity, you can tell me. For instance, the idea of adding default comparison. This is the idea of having, so we already have, by default, you get equal or not equal operators. Well, how about less than, greater than? That's what default comparison is saying. Now, all of that comes as a default as well, too. Does that increase or decrease complexity? Does that make it easier for beginners to use or not? I don't know. It sounds like it does, because now you don't have to work to create greater than and less than. But the natural defaults for these operators is questionable. Is a chair less than a table? I mean, for some things it makes sense, but many other things, they don't really make sense. So yes, the party line is we are always trying to make things easier for non-experts. And the committee, honestly, is in danger of being too expert-friendly, because everybody there is kind of an expert in some ways, right? The reality, whether we take away features or not, is this. We do take away features. The exception specification is one. Registered keyword is another. Does that really decrease the complexity of C++? I personally am dubious whether that really changes a huge amount. Other people are going to have different opinions to that, and I encourage you to speak to them. But we are going to continue our work of slowly taking these features away that are deprecated. But the fact is that I recognize we're never going to take away a major feature. I mean, we're never going to take away templates. We're never going to take away exception handling. Even though there's a large community that wants exception handling to be not used officially. I'll tell you where that comes from. SG14 has a huge embedded community and a games community. Almost none of them use exception handling. You might not use it either. You might turn it off completely. Okay? What should we do? Should we completely remove exception handling? There's a large community that finds that extremely useful, and it is. It's an honestly important part of C++. C++ would not be C++ without exception handling. The question is, how do you serve these diverse communities? The best way that I've been developing this idea along with the various people who wants to not use exception handling is essentially thought about legislating in the library so that they provide both an exception mechanism and a non-exception mechanism. Because right now, the real roadblock is not exception handling in the language, it's that exception handling is infused in the library. And you can't use STL if you don't want to use exception handling in your code. Or you have to do some major surgery on it. And this is why we have libraries like Electronic Arts, STL. Right? We have these different STL libraries. And one thing that we've been thinking about how to do is maybe ask the committee to everywhere add a non-exception approach to every single library. We won't be the first to do that. The networking TS has both approach inside of it. It has both exception handling and a error code return, I think, capability. Okay? And I think some part of the file system also do that. Okay? So it's not going to be the first, and we need to discuss this thoroughly as a committee to be able to enable that. So my answer is we're probably never going to take a huge major feature away, but we might add alongside simplification features that's particularly important for a particular domain, and I can see that happening. other questions? Not just about executors, but about C++ in general, obviously.
Just last questions, because we are ready. The coffee break is ready. So,
just an opinion. In the ECU conference, it's been shown that unfortunately there are a lot of people that still want to program in C instead of C++, especially with embedded systems and so on. Do you think that this kind of feature could try to bring these programs to C++?
Thank you for asking that. I was keynote at the EMBO plus C++ conference, which is an embedded a conference for embedded programming and C++. There are lots of embedded programming conferences, lots of C++ conferences. It turns out there's no conference. This is by Odin Holmes. This was 2 months ago. And that marries both aspects, embedded programming in C++. And I kind of, in that keynote, explained where the failure seems to lie. I'm not necessarily an embedded programming expert, but let me just say that the reason a lot of people have gone to C seems to be, one, a misguided perception that C++ is not performant. It is, okay? But C++ hasn't done a great job in terms of assuring people about the low cost of certain capabilities, the fact that some things are not supposed to be, I forget the name now because I'm blanking out, but that you don't pay for what you use. But the fact of it is that some things you do pay if you don't use it. That's one other thing. To some extent, depending on the implementation, exception and RTTI is one of those things. So we think that we can do a better job, or we can expose those understanding more. But I think the number one thing that we concluded from the EMBO C++ conference is that we need more C++ embedded programming libraries. And there's no repository out there. Because if we have these embedded libraries, and that's why Boost was so useful and so successful, people can just essentially latch onto those libraries. Now, we don't have those embedded C++ libraries, and people are using it even with more complicated ideas, whether it's using executors or whether it's using meta programming. There are embedded libraries that uses meta programming, and they actually do a really good job. Okay? The embedded programmers have them, and this is why one of the things we are talking at SG14 is where to put this repository. Boost could be the place, but they don't have a lot of embedded programmers in their review group. And to some extent, Boost has grown too big. It's almost as unwieldy now. Reviews are taking longer, okay? It used to be a nimble organization, and I'm not trying to put Boost down, and when this goes out on the net, people might start flaming me, but there is some perception that Boost is moving in a direction that might be a little bit opposite. And they're not there yet. I mean, they're still an incredibly good and useful organization. So the embedded programmers have started talking about creating their own repository and instead of going with Boost. Okay? I'm not excluding Boost. I think it's still possible. And this is why we started talking about JFrog and Conan as a repository, who are one of our dinner sponsors. Yes, last night. So it was quite coincidental. So yes, and in this repository, we would people like Odin would start, and other groups from the Dutch group, the Netherlands group, would start putting in embedded C++ libraries like Quasir. Okay, and if we have other people, and we would start doing the reviews in SG14 on these embedded libraries, because that's what we do. And hopefully that would push the growth of embedded C++. I can't really change people's perception. I can't really change your mind. In fact, you probably can't, nobody can actually change anybody's mind, really. If you perceive that C++ is slow, that's never going to change. That's really aren't going to change all that much. What I can do is make these libraries available, make it easy for you to use them for your embedded programs, and slowly you might change your own mind. Thank you very much.